All right, let's dive right into this. Welcome to today's explainer. We're going to take something that usually looks incredibly dense. I'm talking about your standard, intimidating physics laboratory manual, and we're going to decode it into something absolutely fascinating. Today, we're talking all about precision, and not just measuring something small, we're talking about measuring the practically invisible.
So think about this for a second. How do you accurately measure a perfectly clear, incredibly thin plate of glass? Honestly, if you pull out a standard wooden ruler from your desk, you're going to hit a wall pretty fast. The marks on a ruler are just way too far apart. When the thing you're measuring is literally thinner than the gap between those little lines, a normal ruler just won't cut it. You need an entirely different kind of tool. A tool built to magnify the microscopic.
Here's our roadmap for today. 1. The measurement challenge. 2. Decoding the formula. 3. Setting up the experiment. 4. Taking accurate readings. And 5. Final calculations and precautions. Let's get to it. Section 1. The measurement challenge, introducing the apparatus. Okay, our first stop is understanding exactly what this lab manual is actually asking us to do. Straight from the source material, under experiment number 1A, the aim is crystal clear. Determine the thickness of a given glass plate. And to pull this off, the manual gives us our toolkit, our apparatus. First up, the star of the show, the screw gauge. Second, the object we're actually studying, the glass plate. And third, a magnifying lens. Why? Well, because we're dealing with scales that are genuinely going to test the limits of human eyesight.
Section 2. Decoding the formula. Understanding how it thinks.
Now, before we even physically touch the instrument, we have to understand how it thinks. You know how science lab manuals just love to throw intimidating formulas at you on page 1? Well, we are going to break this down. Here is the master equation from our source, the one that eventually spits out our final thickness in millimeters. It says, thickness equals PSR plus N times LC. I know, right now that looks like complete alphabet soup, but actually, every single letter here represents a beautifully simple mechanical movement. Let's decode them. First up, we've got the pitch. The manual defines this as the distance moved by the screw for 5 rotations divided by the number of rotations. Okay, let's use a real-world analogy here. Think of a standard plastic water bottle. When you grab that cap and give it one full 360-degree twist, the cap moves slightly down the threads of the bottle, right? Well, that exact physical distance the cap travels downward in one single full twist, that is the pitch. It's just how far forward the screw drives with one complete spin. Next is LC, or least count. The formula here is the pitch of the screw divided by the number of divisions on the head scale. To really picture this, I want you to imagine taking the absolute smallest tick mark on your desk ruler, that tiny 1 millimeter gap. Now imagine taking a microscopic knife and slicing that tiny gap into 100 even tinier slices. That is basically your least count. It is the absolute smallest possible measurement that this specific tool can confidently record. Finally, we have the variables that actually change based on the piece of glass we're measuring. PSR is the pitch scale reading. You can just think of this as the main, fixed ruler etched right onto the side of the tool. Then we have N, the corrected head scale reading. This is simply the specific, tiny little division line on the rotating handle that happens to line up perfectly with our main ruler once the glass is locked in. Section 3. Setting up the experiment. The pre-flight check. So, with the theory totally out of the way, let's get into the action. Kind of like a pilot before takeoff, we have to do our pre-flight check. The manual gives us these procedural steps to knock out before we even touch the glass. First, we have to note the error and correction of our specific screw gauge. Because tools aren't perfect, sometimes the 0 on the tool is an actual 0, so establishing a baseline is absolutely crucial. Then we note the pitch, count the head scale divisions, and calculate that microscopic least count we just talked about. We are essentially calibrating our minds and our tool. Section 4. Taking accurate readings. The physical procedure. All right, moving into the heart of the experiment. This is where we physically measure the glass plate. The manual lays out these physical steps so logically. Step 1. You'll hold the glass plate between the stud and the screw, and you do it gently. Step 2. You read that main solid ruler line to get your pitch scale reading. Step 3. You look closely to see which tiny rotating line perfectly matches up with the main index line to get your corrected head scale reading, our N variable. And step 4. You just multiply N by our least count to find that microscopic fraction, B. Let's see how this all builds into our actual data table. This is pulled directly from the source, and notice how clean the organization is. Up top, you've got your 0 error. Then, you record your main pitch scale reading in column A. You record your head scale reading to get N. You calculate that tiny fraction in column B. And the grand finale? The final column is simply A plus B.
The main reading plus the microscopic fraction. Boom, you've got your total reading in millimeters.
But here is an absolutely crucial point. A single reading is almost never enough in science. The manual explicitly tells us to take 5 separate readings, physically moving the glass plate around between the stud and screw each time. Why? Well, because glass, especially when you are looking at it on a microscopic level, might not be perfectly flat. It might be ever so slightly thicker on the left edge than it is on the right. So by taking 5 different readings and calculating the mean, we completely average out those tiny imperfections. Section 5. Final Calculations and Precautions. The Quest for Absolute Precision.
Okay, we've collected our data, but now we are entering the final and honestly perhaps the most important phase, protecting our hard-earned data from human error. Our source manual gives us 4 critical precautions. Number 1, no parallax error. Here's a great analogy for this. Picture this. You're sitting in the passenger seat of a car, and you glance over at the speedometer. From your angle, it looks like the driver's going 70, but from the driver's perspective, looking dead on, they're only going 65. That is parallax error. You absolutely must look directly at the lines, not from an angle. Numbers 2 and 3, hold it gently and rotate the screw using the ratchet knob only. This is huge. If you aggressively twist the main barrel, you could literally crush the glass with mechanical force. The ratchet knob is designed to safely click and slip once it makes gentle contact. And lastly, ensure there's no friction. Smooth movements equal clean data.
And with all those precautions carefully followed, we reach our final destination. The manual shows us the ultimate calculation to wrap this up. The average thickness of the glass plate equals the total of all our readings divided by 5. All of those careful turns, those tiny little lines, and precise fractions all funnel down to one perfect, highly accurate number. So what have we learned? By systematically breaking it down, a dense, totally intimidating laboratory manual completely transforms into an intuitive, brilliant system for exploring the microscopic world. We use the analogy of a simple water bottle cap to understand pitch, and slicing up a ruler's lines to understand the least count. Which really leaves us with one final thought to ponder. If mastering a simple twisting screw and a few easy math analogies can completely demystify the invisible thickness of a piece of glass, what else in the universe are we just one tool away from understanding? Thanks for joining me on this explainer, and keep questioning the world around you.